set of summary notes about the states or phases of matter. So the term state or phase is interchangeable. And in the realms of chemistry, we have three major phases or states of matter. You should be able to draw each of their particle diagrams, talk about their particle arrangements, compare their intermolecular forces of attraction, and then in the real world, like when we are handling these types of samples, whether they maintain a definite or fixed shape versus indefinite. So our first particle diagram, because the particles are really close, they're maintaining some sort of order, we would recognize this as a solid. They have very strong intermolecular forces. So I'm going to write the word strong here. And because of those strong intermolecular forces, the particles are held really close, they're maintained some sort of order, and their movement is limited to vibrations. And in our macroscopic world, that when you grab a solid object, its shape is definite, meaning that it remains fixed, and its volume is also definite, it is fixed, that when you pick it up, you're not changing the shape or the volume. We'll talk about entropy in the near future. The most opposite phase of the solid is way over here, where we have a gas phase, and where the gas molecules move as far apart as they possibly can. It's complete disorder, and their movement is rapid and random because they basically have very weak intermolecular forces. And maybe as just a general rule, they might even say that there's no IMAs. Their shape is not fixed or definite because it takes the shape of the container, and the volume is also not fixed because it will move to fill the container. And we'll talk about entropy. So our middle ground is the liquid. So a liquid, the particles stay relatively close, but there's no true order. They flow around, so that's really key. So they have more freedom of movement than the solids. Depending on the liquid, they definitely have stronger IMAs than gases, but tend to have weaker IMAs than solids. Their shape is not fixed. They flow to take the shape of the container, but the volume that they occupied is definite or it is fixed. Now, one of the things that impacts the phase that a sample of matter exhibits in front of us, whether it's a solid, liquid, or gas, is the average kinetic energy of the particles or molecules in the sample. The average kinetic energy, I have taught you to compare that to temperature. So it is directly proportional to, and more specifically, the Kelvin temperature of a sample. So as we see an increase in the Kelvin temperature of the particles in the sample, we see an increase in the average kinetic energy, and kinetic represents the idea of movement or motion. So if we see an increase in the average kinetic energy, we see that all the particle motions, all the particles start to move a little bit more, a little bit more. Typical questions. So here it reads, which sample has the greater average kinetic energy? Now that question sounds super science-y, but if you replace average kinetic energy with the word temperature, it's the exact same question. Which sample has the greater temperature? Well, take a look at your possibilities. You have a sample at 50 degrees Celsius, and you have a sample at 30 degrees Celsius. We are only comparing the temperatures. So 50 degrees Celsius is a greater temperature than 30 degrees Celsius. So A would be the better question. Okay. Next question. When will a 500-gram sample of water have the greatest increase in average kinetic energy. So if it has the greatest increase in average kinetic energy, well, replace average kinetic energy with the word temperature. Which one will have the greatest increase in temperature? So the first thing to take a look at are the temperatures. So this one starts at 10 degrees Celsius and it goes to 20. So there's an increase in temperature. B says it starts at 313 and it goes to 323. So that's an increase in temperature. But when I look at C, it starts at 20 and ends at 10. So that's actually a decrease in temperature. So I know that that's not a good answer. And D, it starts at 323, ends at 313. So once again, that shows a decrease. So that is not a good answer. So now I'm down to A and B. The problem with A and B is it's not a complete direct comparison because A's temperatures are in Celsius and B's are in Kelvin. So you need to change your degree Celsius into kelvins. So on your table T, and we did this back earlier in the school year, the Kelvin temperature is equal to whatever the degree Celsius is plus 273. So 10 plus 273, that means this temperature starts at 283 kelvins. And 20 degrees Celsius plus 273, it's going to go to a temperature of 293 kelvins. Well, the greatest increase in average kinetic energy would mean, even though they both change 10 kelvins, but this one is ending at a much higher temperature. So B is the best answer. Now, materials can go through phase changes, and phase changes are the result of energy transfers. So typically what we understand is if we add heat to the sample, we will at some point, if we add enough heat, we will notice an increase in the temperature. And because there's an increase in the temperature, there's an increase in the average kinetic energy. So the molecules will start to move faster and also apart. And the result is that the IMAs, the attractive forces between the molecules, will start to weaken. Whereas the opposite process is if we remove heat from a sample, and if we remove enough heat, we will ultimately see a drop in the temperature, which means that the molecule's average kinetic energy has decreased, and the molecules will start to move slower. And as they start to move slower, they will also move closer to each other. So the intermolecular attractions, because they're moving slower and closer, they start to strengthen, become stronger. So a quick reminder now, I asked you to draw this type of diagram on your reference tables as a summary. So particle diagrams. So with the solids, if you have to draw a diagram, particle diagram represents a solid. Make sure your molecules are close and they're in order. Where gas is the complete opposite. Your molecules are not touching, there's no order, and you show them moving apart. Where liquid being the middle ground, the particles are pretty close, there's no order in that sample, right? So less order and showing possible some movement in there. Now, if our sample starts off as a solid and it becomes a liquid, it has to gain heat. For a liquid to change into a gas, the liquid has to also gain heat. If we start off with a solid and it's going to change into a gas, completely skipping the gaseous phase, it also has to gain heat. So when we look at this diagram, the direction of the arrows, these all represent that endothermic process, where the sample has to gain or absorb heat. Gain, absorb heat. And when you take a look at the particle diagrams, close ordered, close, no order, not close, no order, okay? So we see that the particles are able to start moving away from each other and farther apart because we see a decrease in their intermolecular attractions. So the big idea here is if your phase change is opposite of the arrows, like a liquid to a solid, well, then it would be opposite energy. It'd be exothermic, a release of heat and a strengthening of the IMAs. Now, a quick little note, you need to know the word that when a solid changes directly into a gas, if you haven't memorized it yet, that means that the sample sublimes. I would expect you to know that when a solid changes to a liquid, we say it melts, and when a liquid changes to a gas, it is boiling or vaporizing.